Can I download the book here? Can I download the physics book here? No. Electricity. Electricity. Yes. Loading. I think these are the ones. Okay. The 30 comments. 12 lines. You can write down this also, right? Here also you can write. How to move it properly. Okay, writing. Okay. It's a value. So, hi, Kaushik.
Hi, sir.
You are having exams also?
Uh, yes. No, sir, I'm coming late from school, so
Oh, okay, okay.
I'm coming from far away, so it takes.
Oh, okay. So today we see electricity, yeah? So Kaushik, today there is no one in the class offline, yeah? Please be active, yeah, in the class. Okay, Kaushik.
Oh,
So what do you know about electricity, Kaushik? Like already, yeah, this it got over, right? Can you say something about what you have learned?
Okay, 1 second. Congrats.
Sure, sir.
Electricity is a form of energy which is used in our day-to-day life and
Okay.
day-to-day life.
Yeah. So what you have learned in this chapter?
So about electric charge, electric current,
Electric charge, electric
resistance,
current,
resistivity,
resistance,
parallel, and
series
series,
connections, parallel connections,
voltmeter,
voltmeter,
volt,
ammeter,
and potential difference.
potential difference,
Then so electric circuit,
Ohm's law, electric circuit. Very good.
Ohm's law. Then and a combination of resistors.
Yeah, combination of resistors that comes under series and parallel connections, right? Also
Then
equivalent resistance,
uh, equal resistance and electric power also.
electric power. Yeah, right.
Yes.
About charge, electric charge. About the resistivity,
Yes.
and yeah, finding voltage and current in the circuit at different branches of the circuit, right? Using a Ohm's law and series parallel
Yes.
connections. So what is this one? This one. This one.
Which one, sir?
So you can see the screen.
Yes, sir.
This one.
So that is the battery.
Battery. Yeah.
Batteries.
Battery or voltage source.
Yes, sir.
What about this one?
Key, sir. Switch key.
This is switch or key, right?
Yes, sir.
What about these?
That those
Resistance.
are resistance.
Resistance which are connected in which connection? Series or
Connecting.
parallel?
This is parallel, sir.
This is parallel connection, right?
Sir, yes,
What
sir.
about this
Parallel.
one? This is also parallel.
Parallel, sir.
So what about this one?
That's ammeter, sir. Meter. Meter.
Meter. Yeah, very good. So these are all connected through. This is wire, yeah, electric wire.
Wires. Wire. Yes.
So what this arrow shows?
So the flow of charges.
Yeah, like flow current
The
flow.
flow
Yeah,
of
like, current flow of current. So these are the things there in that different things, right? Yeah, let's read through this one. Can you read, Kaushik, if you have a textbook like this 11.1 part?
Okay.
11.1.
11.
Yeah.
Yes, sir. Yeah, 1 second. We are familiar with air current and water. We know that flowing water constitutes water current in rivers. Similarly, if the electric charge flows through a conductor, for example, through a metallic wire, we say that there is an electric current in the conductor. In a torch, we know that there's a cell or a battery, when placed in proper order, provide flow of charges or an electric current through the bulb to glow. We have also seen that the torch gives light only when it's switched on. What does a switch do? A switch makes a conducting link between the cell and the bulb. A continuous and closed path of an electric current is called an electric circuit. Now, if the circuit is broken anywhere or the switch of the torch is turned off, the current stops flowing and the bulb does not glow. How do we express electric current? Electric current is expressed by the amount of charges flowing through a particular area in unit time. In other words, it is the rate of flow of electric charges. In circuits using metallic wires, electrons constitute the flow of charges. However, electrons were not known at the time when the phenomena of electricity was first observed. So, electric current was considered to be the flow of positive charges, and the direction of flow of positive charges was taken to be the direction of electric current. Conventionally, in an electric circuit, the direction of electric current is taken as opposite to the direction of flow of electrons, which are negative charges.
Yeah. So, did you get the things from this, Kaushik? What it says? The main thing is about this electric circuit.
Yes, sir. About the switch, about electric
Yeah.
circuit, electric current.
So, what's electric circuit?
Sir, a continuous and a closed path of continuous closed path of an electric current is called an electric circuit.
Continuous and closed path of an electric current is called as an electric circuit. So, what is the role of the switch?
The switch makes the switch. If the switch is turned on, then the flow of charges starts. If the switch is off, the flow of charges stops. Sir. The current won't be passed.
So, what about the electric current? Electric current is the amount of charge flowing through the particular area in unit time.
Current. Yes. Or rate of flow of electric charge.
The rate of flow of electric charges. So I equal to Q by T, right?
This.
So that direction of current is taken as opposite to the direction of the flow of electrons. This is a convention, right? Conventionally, in electric circuit, the direction of electric current is taken as opposite to the direction of the flow of electrons, which are negative charges. So electrons are negative charges. So if net charge is Q, flows across any cross section of a conductor in time t, then the current I through the cross section is given as I equal to Q by T. Net charge flowing through any cross section in time t is given as current I through that cross section. I equal to Q by T. So what's the units of the charge?
Electric charge is coulombs.
Coulombs. The charge units of charge is coulombs. So which is equivalent to the charge contained in nearly 6 into 10 power 8 electrons. Which is equivalent to a charge contained in nearly 6 into 10 power 8 electrons. So 1 electron equal to how many coulombs?
Contain, which is equivalent to
So 1, we know that electron passes the negative charge of 1 electron equal to 1.6 into 10 power minus 19 coulombs. Okay. So 1 coulomb equal to how many electrons? 1 by 1.6 into 10 power minus 19, which is equal to 6 into 10 power 18 electrons.
Yes.
Okay. So 1 coulomb is the charge contained in nearly 6 into 10 power 8 electrons. Because 1 electron equal to 1.6 into 10 power minus 19 coulombs. The electric current is expressed by a unit called ampere. 1 ampere is constituted by the flow of 1 coulomb of charge per second. 1 coulomb of charge per second equal to 1 ampere. Let's say I equal to Q by T, Q equal to 1, T equal to 1, it will be 1.
1 ampere.
It will be 1 ampere.
Yes.
So 1 ampere is constituted by flow of 1 coulomb of charge per second. That is 1 ampere equal to 1 coulomb by 1 second. Small quantities of current are expressed in milliamperes. 1 milliampere equal to 10 power minus 3 amperes. Also microamperes. 1 microampere equal to 10 power minus 6 amperes. The instrument called ammeter measures electric current in a circuit. It is always connected in series. It is always connected in series in a circuit through which the current is to be measured. So here in the figure 11.1 we can see, right? So what are the things here?
So
This
battery,
is cell or battery.
E, ammeter.
This
bulb,
is what? Bulb. This is
ammeter.
ammeter. This is
Yes, sir.
switch or key. So here we can clearly see ammeter is connected in series. Okay. So the current it flows from positive terminal to the negative terminal of the cell. Okay. Electric current flows from positive terminal to the negative terminal. So this is the positive terminal. This is the negative terminal. So flow is like this. Flow is like this. Okay. So here example 1.1. A current of 0.5 ampere is drawn by a filament of a bulb for 10 minutes. Find the amount of electric charge that flows through the circuit. So here I is given as 0.5 amps. What is the time given? 10 minutes.
10 minutes.
Means
600.
10 into 60 seconds. So we need to find out Q, total amount of charge. Q equal to I into T. 0.5 into 10 into 60 equal to 300 coulombs. Right?
Yes.
Calculate the number of electrons constituting 1 coulomb of charge. 1 coulomb of charge equal to how many electrons? Six into 10 power 18 electrons.
18.
Right? Kaushik?
Yes, sir.
He was
Sir, can you hear me?
Yeah, I can hear you. Yeah. So now look at the electric potential and potential difference. Kaushik, can you please read this 11.2, section 11.2?
What makes the electric charge to flow? Let us consider the analogy of flow of water. Charges do not flow in a copper wire by themselves, just as water in a perfectly horizontal tube does not. If one end of the tube is connected to a tank of water kept at a higher level, such that there is a pressure difference between the two ends of the tube, water flows out of the other end of the tube. A flow of charges in a conducting metal wire, the gravity, of course, has no role to play. The electrons move only if there is difference to electric pressure, called the potential difference, along the conductor. This difference of potential may be produced by the battery, consider, consisting of one or more electric cell. The chemical action within a cell generates the potential difference across the terminal of the cell, even when no current is drawn from it. When the cell is connected to a conducting circuit element, the potential difference sets the charges in motion in the conductor and produces an electric current. In order to maintain the current in a given electric circuit, the cell has to expend its chemical energy stored in it. We define the electric potential difference between 2 points as in an electric circuit carrying some current as a work done to move a unit charge from one point to other. V is equal to W by Q.
Yeah. So what it says about potential difference?
Sir, when the electrons have when the electrons move, they should move in a difference of electric pressure called the potential difference.
Yeah, right.
So this
How this potential difference is applied to the battery consisting of one or more electric cells. Who is this?
Hari.
Yeah, Hari.
I joined just now.
Okay, Hari. Why you are late, Hari?
No, sir, I had to go out, so just now I came home. So.
Okay. So yeah, how the potential difference is generated, applied, Kaushik? Through the battery. Potential difference is applied through
battery
consisting of one or more electric cells. So how this potential difference is defined mathematically? The potential difference between 2 points in an electric circuit is equal to work done to move
electric
work done by charge.
Yes.
This is potential difference V. Okay. So the units of potential difference is volt, named after Alessandro Volta, an Italian physicist. 1 volt is potential difference between 2 points in a current carrying conductor when 1 joule of work is done to move a 1 charge of Coulomb. So work is measured in, what are the units of work done?
Joules, sir.
Joules or joules.
Joule.
So 1 joule by 1 Coulomb equal to 1 volt, right? So 1 volt is the potential difference between 2 points in a current carrying conductor when 1 joule of work is done to move a charge of 1 Coulomb from one point to other. The potential difference is measured by means of an instrument called voltmeter. Okay. So what is the instrument for current? Hari?
Sir, yes, sir.
So what is the instrument to measure current? Kaushik?
Sir, is it voltmeter?
Voltmeter is for to measure the potential difference.
Okay, instrument measure current.
Yeah.
Sir, can you hear me?
Kaushik is there?
Yes, sir. Yes, sir. I have network issue.
Okay. That's ammeter, right? So voltmeter is always connected in the
Yeah, yes,
parallel.
sir. Ammeter.
Voltmeter is always connected in parallel across the points between which the potential difference is to be measured. Ammeter is always connected in series. Ammeter is connected in series. Voltmeter is always connected in parallel. Okay, Hari.
Okay, sir.
So yeah, problem 11.2. How much work is done in moving a charge of 12 coulomb across 2 points having a potential difference 12 volt? What is the formula for volt? Potential difference V equal to Q by
What is your work done by
Q, right?
charge? Yes, sir.
So now we need to find out work done. Work done equal to V into Q.
V into Q.
What is V here? 12.
V is 12.
Q
2
is
means
2.
24 joules.
24 joules. Right?
Yes, sir.
Twenty-four joules. Yeah. So how much energy is given to each coulomb of charge passing through a 6-volt battery?
How much energy is given? Energy means 6 4. Energy is given. Sir, 6, sir.
Yeah, 6 joules, right?
6 joules, sir.
What is meant by saying that potential difference between 2 points is 1 volt?
Sir, the amount of work done to carry 1 unit of charge from one point to another.
The amount of work done. No, not amount of work done to. It's like one work done is one joule, right?
Yes, sir.
So what here says is 1 volt is the potential difference between the 2 points in current carrying conductor when 1 joule of work is done. 1 joule of work is done to move a charge of 1 coulomb. Okay. Because V equal to W by Q 1 equal to 1 by 1. One joule of work done when moving a 1 coulomb of charge. So 1 coulomb of charge contains how many electrons?
6 into 10 power 18.
6 into 10 power 8 electrons. So 1 electron equal to 1.6 into 10 power minus 19 coulombs. 1 coulomb equal to 6 into 10 power 18 electrons. The next is the circuit diagram. So we know that an electric circuit as shown in figure 11.1 comprises a cell or a battery, a plug key, electric components, connecting wires. It is often convenient to draw a schematic diagram in which different components of the circuit are represented by symbols conventionally used. Conventional symbols used to represent some of the most commonly used electric components are given in table 11. So electric cell is represented with two vertical bars with a plus or minus. Plus is with a larger height, minus is with a smaller one. connecting both of them. Okay, this is electric cell. What about battery? Battery is a combination of electric cells. So plus minus, plus minus, plus minus. So finally, you can neglect this middle ones. You can directly say this side is plus, this side is minus. So plug key or switch is when it is open. When it is closed, we need to keep a dot. Okay.
Yes, sir.
A wire joint is, so this is a wire joint. Wire crossing. Crossing is, we need to show like this. If it is joint means, directly we draw one above the other. If it is crossing means, we'll show like this. We can show like this or we can show like this. Both are correct. Okay.
Okay.
We can show like this also, or we can show like this. Both are right. Then bulb. Electric bulb is represented with like this. Okay. Resistor. A resistor of resistance R with resistance R. Okay.
Yes, sir.
Variable resistance or rheostat represented with. So this shows that resistance is varying. Or also we can say that we can keep something like this here. Both represents variable resistance or rheostat. So ammeter is plus minus. Voltmeter is also plus minus. So these are the electric circuit symbols. Symbols of different electric components.
Yes.
So now we look at Ohm's law. Ohm's law is, so we have seen the potential difference. We have seen the current. Now Ohm's law gives the relation between the potential difference and the current. Okay.
Okay,
So
sir.
Kaushik, can you read this activity 11.1? Just read it out.
Yes.
11.1.
Set up a circuit as shown in figure 11.2 consisting of nichrome wire XY of length, say 0.5 meter, an ammeter, a voltmeter, and 4 cell of 1.5 volt each. Nichrome is an alloy of nickel, chromium, manganese, and iron metals. First, use only one cell as the source, in the circuit. As the source in the circuit. Note the readings in the ammeter. Note the readings in the ammeter. One for the ammeter. For the current and reading of the voltmeter V, or for the potential difference across the nichrome wire XY in the circuit. Tabulate them in the table given. Next, connect two cells in the circuit and note the respective readings of the ammeter and voltmeter for the values of current through the nichrome wire and potential difference across the nichrome wire. Repeat the above step using 3 cell and then 4 cell in the circuit separately. Calculate the ratio of volt to current for each pair of potential difference, volt and current I.
So here XY of length 0.5 meter. This is made up with nichrome wire. So this will act as a resistor. Okay. This nichrome wire of 1.5 meter or 0.5 meter, it will act as a resistor. So we have the voltage cells, which are of each one is of 1.5 volts each. We have 4 cells. Each cell is 0.5, 1.5 volt. So to measure the voltage, we have connected the voltmeter in parallel. To measure the current, we have connected the ammeter in series. And there is a plug key or switch which is connected, which is closed, right? So the current will flow from positive to negative. That's why direction is like this. So if you consider the resistance is R, if you connect a one source which is 1.5 volt, V equal to 1.5 volt, what's the current, Kaushik?
If V is equal to
1.5 volt, current will be
5, I understand, sir.
so what's the Ohm's law? V equal to
V is equal to I by R, sir. IR.
IR, right?
IR.
So V equal to so I equal to 1.5 by R. Here resistance is R. We don't know the value, right?
Okay.
So if V equal to, if you connect two cells together, then what will be the I? If you connect two cells together, what will be the I? So what will be the voltage if I connect two cells together?
3, sir.
Sorry,
3, sir.
3, right?
Yes, sir.
So then I will be 3 by R.
Okay.
If you connect three cells together, I will be
4.5 by R.
4.5 by R. 4 cells, 6 by R.
6 by R.
What about voltage across R? When I connect one cell,
What, sir?
if I connect one cell, what will the voltage across R?
Oh, sir.
Or potential difference across R? The source is 1.5 volt. The potential difference across R also 1.5 volt because there is only one element, no? Right?
Yeah.
Okay, if you consider I equal to 1.5 by R, okay? Then how can we calculate the voltage across resistance R? V equal to IR, right?
Yes, sir.
1.5 by R into R. R cancel, it will be 1.5 volt. Okay.
Okay.
So if I connect two cells, then it will be 3 volt. That will appear across the resistor R. So now we look at the Ohm's law.
So can I just drink water and come, sir?
Yeah, please. Hari, you are there, right?
Sir, yes, sir.
Kaushik, are you back?
Can you hear me, sir?
Yeah. So yeah, what the previous activity says is that when we increasing the voltage potential difference, it says that current also will increase linearly.
Okay.
So that's how through that activity we will come to know that V is proportional to I. Okay. And V by I is constant. That constant is resistance. So V equal to IR. That's the Ohm's law. So this is called VI graph. So left side you are seeing, right? This is the VI or IB graph. So as you increase the voltage, current also will increase. Or as you increase the current, voltage also will increase. So V is proportional to I. So this is called Ohm's law. So the potential difference V across the ends of any given metallic wire in an electric circuit is directly proportional to the current flowing through it, provided its temperature is constant. Provided its temperature remains the same. So what's the Ohm's law?
The potential difference V when it's across in the two ends and in the ends of the wire in the electric circuit, it is directly proportional to the current flowing, which is provided and it's provided by the temperature. It remains the same. So this is
Provided that the temperature remains the same. The condition that when the temperature is constant, then the potential difference across any conducting wire will be directly proportional to the current flowing through the metallic wire. So V equal to IR. R is a constant for a given metallic wire at a given temperature and is called resistance. So R will vary if the temperature varies. R will change if the temperature will change. But if the temperature is constant for a given wire, the R will be constant. It is a property of a conductor to resist the flow of charges through it. So R will be V by I. If the potential difference across two ends of a conductor is 1 volt and the current through it is 1 ampere, then the resistance is 1 ohm. So resistance is measured in terms of what are the units of resistance? Ohms. Resistance of potential difference is volts. The units of potential difference volts. The units of current are amperes. So 1 ohm equal to 1 volt by 1 ampere means the potential difference across the two ends of the conductor is 1 volt and the current through the flowing through conductor is 1 volt and the resistance R is 1 ohm. Also current through the resistor, so we can see that I equal to V by R. So I is inversely proportional to resistance, right?
Yes, sir.
Current through resistor is inversely proportional to its resistance. The resistance is doubled, the current gets halved. In many practical cases, it is necessary to increase or decrease the current in an electric circuit. A component used to regulate the current without changing the voltage source is called variable resistance. So if we change the resistance, the current will change. So using the variable resistance, we can change the current in the electric circuit. In an electric circuit, the device called rheostat. Rheostat is often used to change the resistance in the circuit. We will now study about the electrical resistance of a conductor with the help of following activity. So what the activity says, Hari, do you have textbook? Or can you read it from the screen? Activity 11.2. Hari is there. Okay, Kaushik,
Yes,
please
sir,
read,
yes,
yeah, 11.2.
Sir, I'll
Yeah, please read, Hari.
11.2.
Yeah.
Take a nichrome wire, a torch bulb, a 10-volt bulb, an ammeter, 0 to 5 range, a plug and a plug key and some connecting wires. Set up the circuit by connecting 4 dry cells of 1.5 V each in series with the ammeter, leaving a gap XY in the circuit as shown in figure 11.4.
Figure 11.4. Okay. Okay, yeah, now.
If you read this,
Yeah,
connect the circuit by connecting the nichrome wire in the
complete.
gap.
Complete the circuit.
Oh, complete, yeah. Complete nichrome wire in the gap XY. Plug the key. Note down the ammeter reading. Take down the key from the plug. Note, always take out the key from the plug after measuring the current through the circuit. Replace the nichrome wire with a torch bulb in the circuit and find out the current through it by measuring the reading of the ammeter. Now repeat the above step with the 10-volt bulb in the gap XY. Are the ammeter reading different for different components connected in the gap XY? What do the above observation indicate? You may repeat this activity by keeping any material in the gap. Observe the ammeter reading in each case. Analyze the observation.
So from this experiment, what we'll get to know?
Sir, we get to know that like in a nichrome wire gap XY, are the readings same for a torch bulb, a 10 volts torch bulb and a 10 watts bulb? Are the readings same or are they different? We are going to observe it.
So every bulb has its own resistance. Let's say for nichrome wire, it's resistance, and 10-volt bulb head, it has its own resistance. Okay. So when the resistance will change, current also will change. So this activity, we observe that the current is different for different components. Okay. Why do they differ? Certain components often an easy path for the flow of electric current, while others resist the flow. We know that the motion of electrons in an electric circuit consists of an electric current. The electrons, however, are not completely free to move within a conductor. They are restrained by the attraction of the atoms among which they move. Thus, motion of electrons through a conductor is retarded by its resistance. A component of a given size that offers a low resistance is called good conductor. A conductor having a same appreciable resistance is called resistor. A component of identical size that offers a higher resistance is a poor conductor. An insulator of the same size offers even higher resistance. So here there are two things, right? Three things. One is a good conductor. Next is a poor conductor. Next is insulator. So good conductor offers a low resistance. It offers a low resistance. Poor conductor, it offers high resistance. Insulator, it offers even higher resistance. Okay. This is what we need to understand. Yeah, Kaushik, can you read this activity 11 point? This one.
Sir,
11.3?
Kaushik left, sir. Kaushik left.
Left, huh? Okay. You read, Hari. 11.3 also. Activity 11.3.
Sir, 1 minute, sir.
Yeah.
Complete an electric circuit consisting of a cell, an ammeter, and chrome wire of length L, say mark, and a plug E as shown in figure 11.5.
Yeah. This is the figure 11.5.
Now, now plug the key, note the current in ammeter, replace the nichrome wire by another nichrome wire of same thickness but twice the length, that is 2L. Note the ammeter reading. Now replace the wire by a thicker nichrome wire of the same length L. A thicker wire has a larger cross-sectional area. Again, note on the current through the circuit. Instead of taking a nichrome wire, connect a copper wire. In the circuit, let the wire be the same length and the area of the cross-section as that of a first nichrome wire. Note the value of the current. Notice the difference in the current in all cases. Does the current depend on the length of the conductor? Does the current depend on the area of cross-sectional use of the wire used?
Yeah. Thank you, Hari.
Sir.
So here, so what that experiment says is that, so it is observed that the ammeter reading decreases to 1/2 when the length of the wire is doubled. So when the length of wire is doubled, ammeter reading will become 1/2. So the ammeter reading is increased when the thicker wire of the same material and of the same length is used in the circuit. A change in ammeter reading is observed when a wire of different material of the same length and the same area of cross section is used. On applying Ohm's law, we observe that resistance of a conductor depends on its length, on its area cross section, on the nature of the material. Precise measurements have shown that the resistance of a uniform metallic conductor is directly proportional to its length. So resistance will be proportional to length, and resistance will be inversely proportional to 1 by area, inversely proportional to area. So the resistance will be proportional to L by A. So the proportionality constant is rho. This is the material property. Rho is called resistivity, and it's a material property. Rho is a constant of proportionality and is called electrical resistivity of a material of the conductor. The SI unit of resistor is, resistivity is ohm meter. Because let's say you can take as R equal to rho into L by A, rho equal to R into A by L. So R has this has ohm, units as ohm, area has units as meter square, length has units meters, so meter square meter will get cancelled, so ohm meter. Okay, resistivity has units ohm meter.
Sir, can I leave the meeting? Sir,
just a 2 minutes, yeah, 2-3 minutes will close.
yeah.
So the SI unit of resistivity is ohm meter, and it's a characteristic property of the material. It's a characteristic property of the material. The metals and the alloys have very low resistivity in the range of 10 power minus 8 ohm meter to 10 power minus 6 ohm meter. Metals and alloys have very low resistivity. They are good conductors of electricity. Low resistivity means they are good conductors. Insulators like rubber and glass have resistivity of order of 10 power 12 to 10 power 17. So here we can see it's very low. Here we can see it's very high. So both the resistance and resistivity of the material vary with temperature. So both will vary with the temperature. So table 11.2 reveals the resistivity of an alloy is generally higher than of its constituent metals. Alloys do not oxidize readily at higher temperatures. For this reason, they are commonly used in electrical heating devices like electric iron, toasters, etc. Tungsten is used almost exclusively for filaments of electric bulbs, whereas copper and aluminum are generally used for electrical transmission lines. So these are the electrical resistivity of some substances at 20 degrees. So till this point we close, and we can do the things later, like next week. Okay, Hari.